All right, well, welcome everyone. I am JJ. Second example problem. So we are saying let's find z bar for our object shown. We're really just doing a 3D centroid in here. We're only finding z bar for this because everything's circular on that. The centroid of a circular is in the middle. X bar and Y bar are both right at the origin. They'd be 0. So we're just simplifying that and saying let's only find z bar in here. So if we're doing this, I need to figure out how do I break this up into pieces I can work with. Again, there's centroid tables probably in the back of your book or a bunch available online. But we could come in here and say, let's start laying out our table as we do this. We have realistically a truncated cone. Our tables normally don't have a truncated cone shape, but I could come in and extend that. I would get a big cone in here that I can work with. I'll use that for my first shape in here. That'll be a positive shape for everything. Our big cone. So in my table, I can start setting up my table in here. I'll have a big cone. Big cone. That's going to be a positive shape for us. This is our shape or our part number. I'm just going to name them in here. If I do that, that cone goes from that XY plane up to the tip in here. I've added in content in that. Really, there's no cone up at the top of this. That means I need to subtract something off from that. So my second piece, let's call that my small cone. Small cone. And that one's going to be negative. That'll be another piece for us. We have in here a cylinder. That dashed line is trying to show it's been bored out from the middle of our truncated cone, but it stops at the hemisphere in here. So a cylinder will be another shape. Cylinder. And that is also negative for us. At the very bottom of that, below the XY plane, we have a half sphere or a hemisphere. Hemisphere. And that one is positive for us. And at the very bottom, we need to sum everything up. So we'll get a summation row in there. If I'm trying to find z bar, the equation I really am ending up looking at in here, just like we were able to do x bar and y bar, I can trade in z's for everything. My z bar should just be, z bar is the sum of my z tilde v divided by the sum of my volumes. Divided by the sum of the volume. So let's go ahead and fill in my table. Sum of the volume. To see what we need to get in here. So I need a column for every variable that showed up in this. So I need volumes in this. So it's my volume. And that's going to be in, I have millimeters, so I'm going to get millimeters cubed. My next piece, I have a z tilde. So z tilde. And that's going to be in millimeters for us. Once I have z tilde, I can multiply it by the volume to get z tilde v. And we're not going to get thrown off by the units on this. Logically, if we have millimeters cubed times millimeters, my units here are going to be millimeters to the fourth. Now, what is a millimeter to the fourth? It's an engineering property that we're going to end up working with. Don't overthink this. That's our units that come out. Also in here, as I start dealing with millimeters, we're going to get really small or really big numbers coming out for everything. I'm going to do this times 10 to the sixth. Millimeters cubed for the volume. And again, times 10 to the sixth millimeters to the fourth for that z tilde v in there. Just to make the units a lot easier to work with so we can drop off a bunch of stuff. But let's come and work with this. So the first thing I have is my big cone. The area or the volume of a cone is pi r squared h divided by 3. And right now, I don't know the height of that cone. I know the height of a truncated cone, but not the entire cone. But I can find that height of the cone using proportional triangles for everything in here. Let's make a quick picture. So if I draw, it'll look like a triangle, from the left edge to the center. And then I can go up. Really, this is my cone in here. If I resolve this, around the z-axis, I would get a cone out in here. At the bottom, my radius in here, it looks like I'm not given radius, except I know from that xy plane to the bottom of my hemisphere is 50 millimeters. That's the radius. From one point from the center to any point on the outside edge is the radius, 50 millimeters. So I know this is 50. And I can draw in where I truncate this at. I truncate it, we'll say here. At that point, I've gone up 100 millimeters. So I'll add that distance in. And I know my radius at that point is the cylinder's radius, 25 millimeters. 25. And let's call this last distance y. I can use proportional triangles. My ratio of height to base in this little triangle, that truncated cone portion, y over 25, should be my ratio of height to base in my big triangle, or the entire big cone, equals y plus 100 divided by 50. Which, if we solve for y, we're going to get the y is also 100. Y equals 100 millimeters, which would be our height here. That isn't the height of our big cone. The big cone would be y plus 100, 200. So pi times our radius of the big cone, 50 squared, times our height, 100, 200, divided by 3. We're going to get 0.524 times 10 to the 6th cubic millimeters. 0.524. Our next one, that small cone, is the exact same formula, except we're negative here. Negative pi times our radius squared times the height over 3. Or negative pi times the radius is 25 times our height, just y, 100. Negative pi times our 25 squared times 100 over 3 would get us negative 0.0654 times 10 to the 6th cubic millimeters. For our cylinder, well, the volume of an entire cylinder is pi r squared h. So this is negative. We just make that negative. Negative pi r squared h. The radius of that cylinder is 25. The height is 100. So negative pi times 25 squared times 100 will get us negative 0.1963. And finally, our hemisphere. An entire sphere has a volume of 4/3 pi r cubed. So half of a sphere would be half of that. Or 2/3 pi r cubed. We'll write that as 2 pi r cubed over 3. Where our radius is 50. We know it. This is going to get us 0.262 times 10 to the 6th cubic millimeters. Which, adding all of that up, we get 0.524. 5243 times 10 to the 6th cubic millimeters. And then we can come in and deal with our z tilde values. So we're measuring from some common point. Let's measure from that xy plane, from the origin in here, to the centroid of each piece. For a cone, our z bar or z tilde is height over 4. So for our big cone, that height would be y plus 100, 200, 100 plus 100 is 200, divided by 4, 50. For our small cone, we would be at 100 divided by 4. Still just, or not quite that. We would be at, from the xy plane, I need to go up 100 to get to the start of the small cone, and then I can go height over 4 into it. So 100 plus 100 over 4 is 125. For the cylinder, we just need to get to the middle of it, so just height over 2. H over 2. 100 over 2, 50. And the hemisphere. From the flat side of our hemisphere, so from the xy plane, we would measure 3r over 8. 3r over 8. But there's one tricky thing in here. Because we're measuring that xy plane is at the origin, at the flat side, and we're going down below that, we got to make this negative. we're measuring in the negative z direction. We're dropping down to get to the centroid of that hemisphere. So negative 3r over 8 will get us negative 18.75. Negative 18.75. And we don't need to add that one up. But then I can just come in and multiply these together, accounting for the unit difference, times 10 to the 6 millimeters, and millimeters here. We will get times 10 to the 6 millimeters out when I write this. We'd have 26.2. Negative 8.175. Negative 9.815. Negative 4.91. And our total here would sum up to be 3.3 times 10 to the 6th millimeters to the 4th. Which we can come in and find z bar then. Our z bar should be equal to, z bar is our total z tilde v, 3.3 times 10 to the 6th, divided by our total volume, divided by the sum of our v, divided by 0.5243. Yeah, 43 times 10 to the 6th. In this, those times 10 to the 6th, those are going to cancel out. And we have just 3.3 over 0.5243. Our z bar we end up getting is 6.29 millimeters, which would be our final answer in here. Again, just make sure you can make our tables in here. Follow any centroid table. We can look these up online. They're in books, in pretty much every statics book, and pretty much a lot of our engineering books actually have centroid tables in here. Be able to work with them. But hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around, watch more videos. Let's get you an A with JJ.